Okay, welcome back, everybody. Just a quick note. Today we will finish chapter 6, possibly jump into 7 a little bit, probably. And next week we have you have exam 2, chapters 4, 5, and 6. Okay, similar format, nothing complicated. I mean, we'll keep it straight and narrow. I don't know how many questions, but I suspect there's about the same number. Okay, multiple choice, short answer. All right, and come Tuesday, as always, if there's not any questions concerning those chapters, I'll just continue with the lecture. Okay, with whatever chapter we're at. All right, any questions? All right, no surprises, right? Okay. Well, let us continue with chapter 6, and we were this chapter dealing with the periodic table and some properties of elements. Okay, some periodicity, as they call it, hence the periodic table. There are properties there that the elements are placed in the same group because they exhibit a similar type of reactivity. And it turns out that's because they share the number of valence electrons. Okay, so let's talk briefly about the atomic size. All the atoms have a radius or a diameter, okay, but the radius is the distance from the estimated distance from the nucleus, center of the nucleus, to the outermost shell, the outermost electron. Okay, now, as we go down the periodic table, the radius increases, which, if we look at the periodic table, definitely makes sense, right? Because we're here being in groups, the energy levels, we got 7 energy levels. And so the difference between, let's say, potassium and lithium, what they have in common, first of all, is they have 1 valence electron, okay? Lithium has 3 electrons total, okay? Potassium has 19 electrons total. So just by that, and plus 19 protons for potassium and 3 protons for lithium, just that in itself will tell you that lithium is much smaller than potassium. But furthermore, since they all share 1 valence electron, see, 1 electron. So lithium, of the 3, 1 electron is in the outermost shell for both of these guys, except for potassium, that 1 electron happens to be in the 4th energy level. So it's further out in diameter. So it makes sense that as we go down the periodic table, the radius increases, the element size increases, simply because we're getting into bigger elements and greater energy levels. Where they differ with respect to radius is that when we go across the periodic table, okay, across the periodic table. So this is something like, let's compare silicon versus chlorine. Well, what they have in common is both of them are in the 3rd energy level. That is, their valence electrons are in the 3rd energy level. Yes, chlorine has 4 of them in the 3rd energy level, and chlorine has 7 electrons in the 3rd energy level. So they differ in that sense, okay? Even though they both had the commonality of their outermost shell is in the 3rd energy level. The other aspect about them is that they differ, obviously, is that silicon has 14 protons, okay? Whereas chlorine has 17 protons, okay? And obviously, silicon also has 14 electrons, and the chlorine has 17 electrons. Well, where they differ, obviously, is the number of protons. Chlorine has a greater number of positive charges, okay, and also a greater number of negative charges. The net effect is the force, what is called the nuclear force for chlorine, is much greater than it is for silicon. The result is having more positive and more electrons, that force is greater, and it tends to pull the electrons, all of them, into itself much greater than for silicon, resulting in that chlorine is a much smaller, has a much smaller radius compared to silicon, okay? Again, that is because chlorine has more positive charge, more what is called nuclear force than silicon, resulting in the electrons being pulled into itself much greater. The fact that it's pulling those electrons much greater, chlorine that is, tells you, furthermore tells you that chlorine is holding on to electrons with a tighter grip than silicon, okay? And therefore, to remove electrons is going to be a lot more challenging for chlorine than, say, silicon. And so the general trend, let's go back, of the radius across the periodic table is that if we go from, if you go, you want to call it left to right, right to left, okay. As in my case, if I go from left to right, the radius gets smaller. If you go from right to left, the radius gets bigger. Tomato, tomato, it's the same effect, either direction you want to call it. Your book says here, increases from right to left. Yes, the radius gets larger. Again, because the number of protons increases, and we have a more, what is called the nuclear force occurring for those elements that have a greater number of protons. And therefore, the electrons are pulled in closer and actually causing the radius to get smaller, okay? And so a general trend to help you out is this little snowman that we have here, meaning that circles the head, the body, and the torso, the mid, and the bottom, I should say. That circular represents the radius, okay? And so you can see as you go down the periodic table, the radius gets larger. And then if you take that same snowman and knock him over to the side, that means from left to right, the radius gets smaller because of the nuclear force that's occurring when the molecules start increasing the number of protons from left to right, okay? So that's the general trend. As with any general trend, it's not always everything's 100%. I believe me, there's nothing ever 100% in science. There's always exceptions to the rules and slight changes. It's, we don't have anything that's 100%. So, but this little screen here kind of gives you the general trend, kind of a relative picture of the elements as we go down the periodic table. You can see the elements get bigger, okay? And as you go from left to right, you can see that the radius has a general trend of getting smaller. Now, with the other elements, the intertransition metals and so forth, these out here, you can see that it really doesn't, the trend is somewhat in that direction. And the same for the lanthanides and actinides and so forth. And the d electrons, the general trend still continues, but there is some subtle differences, but that's okay. The trend for Chem 130 is down the periodic table, radius gets bigger, left to right, radius gets smaller, but what's important is why, okay? You'll be asked questions, I'm sure someplace, somewhere, that they're asking you why, what is the trend from top to bottom, or bottom to up, either way. And then the next part is explain why, okay? Not stating just the trend, but an explanation as to why that trend does occur. All right, so let's take a look at 3 elements, okay? And the question is which is larger, which has a larger radius. So we have the three elements here: oxygen, beryllium, deuterium. And the question is, well, the first thing we need to do is find them on the periodic table, okay? Because that's going to help us understand. Now, we can go and Google it and find out the radius, but they're not necessary. Just find it on the periodic table. All right, we find them and we see that they're in group 6A. All right, and so that means we're going down the periodic table. We can say that the last one here is much bigger simply because it is in the larger, the valence electrons are in the larger energy level. Okay, and so it is much bigger. Now, with respect to magnesium, silicon, and sulfur, same answer here to begin with is first find them on their periodic table. All right, and in doing so, we find them right here. So all of them have in common, they're on the same period, same energy level. So we have to look at the next thing. If they're on the same energy level, that means that we need to figure out who's got the greater number of protons. And here, sulfur has a greater number of protons, so its diameter is going to be much smaller than silicon and magnesium, right? Because again, sulfur has a lot more protons and electrons, and therefore that nuclear force is much greater, and those electrons are being pulled into itself much greater than compared to magnesium, okay? And if you think about it again, magnesium, with those electrons being held further away from the nucleus, they're much more readily would be removed or lost, which is consistent with magnesium being a metal, tends to want to lose electrons, okay? For at least a couple of reasons. One, it's got two valence electrons and it's a metal and it's going to lose those two electrons. Second of all, those two electrons are literally further way out there in the valence shell, and it just takes up more energy. It takes more energy to maintain them, okay? And there's less nuclear force occurring in magnesium, and therefore those electrons in the outermost shell are more readily given, are able to be given up. All right, so let's continue. So there are videos on atomic size. Dr. Kim has a good video on her discussing the subject. So you make sure you listen to her. You'll see it's another perspective, another means of explaining this particular topic. All right, now all tied in with respect to the radius and why the radius gets smaller, and related to how big they are relative to where they're at in the position of periodic table, and how many protons and electrons are there to give more nuclear force. All that's related to why certain elements have this particular property called ionization energy, how some of them are greater in energy compared to others. So what exactly is ionization energy? And it's defined as follows, okay? First of all, we're looking at a neutral atom. So we're looking at an element, okay? And then it is placed under conditions so that it tries to remove an electron, okay? And so the process is shown in this equation here, where you got the elemental sodium, in which energy is put into the system and measured. And we are trying to do is to remove an electron, okay, to create an ion. So that is hence the term ionization energy. How much energy does it take to ionize that element? Okay, is what we're talking about here. We're going to be talking about a different property called electronegativity, which is totally different. Okay, this we don't want to confuse the two. Here we're just taking a neutral element, we're trying to remove an electron. And so given the trends we've been talking about, you might start thinking, well, wait a minute, let's think about this. Since a noble gases are very stable, and they have the octet, including helium, which has a duet, could anticipate that the noble gases are going to require a lot of energy to remove an electron. And that's a general trend you can start thinking about. Okay. The other aspect, what we talked about, is that metals tend to lose electrons compared to nonmetals. So that in itself suggests that when it comes to removing electrons and measuring the amount of energy it takes, that for metals is going to be much less energy than for nonmetals. Okay. Also, with a lot of the nonmetals along the same period, we know that as you go across the periodic table, you pick up the number of protons, you pick up the number of electrons, and that nuclear charge, if you will, that attraction gets more stronger. Hence, they're going to take a lot of energy to remove an electron. So given everything we talked about, we can look at the ionization energy, and it starts to make hopefully sense. Okay. So ionization energy increases up a group. Okay. Well, let's break it down. Let's take a look at the periodic table. And so what that's saying is this, that if we were to compare, let's say the IE for lithium versus potassium. Okay. All right. So it's saying here that the ionization energy, the IE for lithium, is greater than potassium. Okay, well, let's walk this through. Point number one, okay, but lithium, it only has 3 electrons, okay, and potassium has 19 electrons. And so that in itself, the nuclear force, you might think it may have a fact, but let's just put that to the side for a bit. The nuclear force, remember, going across the periodic table? More than likely, that's not the case, okay? All right, so point number 2, they both have 1 valence electron in the outermost shell, okay? With lithium having a total of 3, and potassium have a total of 19. But both of them have 1 valence electron on the outermost shell. Where they differ is this: lithium has that 1 electron in the 2nd energy level, compared to potassium that has that 1 electron in the 4th energy level. So therefore, if you think about it, for lithium, that valence electron is much closer to the nucleus than that valence electron for potassium, which is 4 energy levels away and is further away from the nucleus. So the interaction between the valence electron for potassium is much less, the interaction being with the nucleus and that lone electron, than it is for lithium, whose electron is closer to the nucleus. Okay. Basically, think about it. I'm the nucleus, my electron is, a mile away, and I represent lithium, or I'm the nucleus of potassium, and that valence electron is 5 miles away. Okay, so that interaction with that 5 mile away electron is much less, not as strong as the interaction with that electron that's a mile away, and that's what's happening here. And hence, that's why lithium has an ionization energy much greater than potassium. And that is true going down the periodic table for all the elements. Okay. Now, as we go from left to right, the ionization energy level increases. Okay. We had talked about the radius as we went from left to right, how it went up. We explained that by the fact that if we went from left to right, we increased the number of protons and electrons. And so we increased that nuclear force, okay, resulting in the radius shrinking in, because the electrons in the outermost shell are being pulled in much greater. okay, much tighter than the elements going to the left on the same period. Okay? Eventually, we get to the noble gas, and those electrons are really being held on to. Why? Because the noble gases have that stable, magical 8 electrons around its Helium shell. Okay. Furthermore, nonmetals have a tendency to have a higher ionization energy. Why? Because they want to lose electrons. That's their tendency to lose electrons. In contrast to metals who want to, did I say lose? I apologize. Non-metals want to gain electrons, okay? They don't want to lose them. Non-metals want to gain electrons. So the likelihood of giving them up is much lower. It's going to require a lot more energy. In contrast to metals that want to lose electrons. And therefore, the amount of energy to knock off an electron would be much less for metals. All right, so if we were to plot the data of taking each element and measure its specific ionization energy, we'll see the following trend, okay? Let me just talk you through it. If we look at the first data point, which is right here, that is hydrogen, far left, number 1, okay? Now, as you go across the periodic table, we have helium, okay? So helium now, its outermost shell is full. Remember, helium has a duet rule. And so when I compare within that period, that's a trend from left to right, the ionization energy goes up. Hydrogen has somewhere around, the scale here is ionization energy, electron volts, okay? So you can see you've got 10, 11, 12, 13, maybe a 13 and a half, 13.5 EVs for hydrogen. And then for helium, it jumps up to about 24.5. Big old jump as we come across. All right. So we're at helium right here. And then we go back to the second period and we're back to the metals, which is lithium. And there's lithium right here. And so lithium being a metal, okay, it's going to give up its electron, very readily, and the energy drops about 5. As we shoot across the periodic table, this trend is consistent with the radius. As they get smaller from left to right, the electrons are being held on tighter until you get to neon, which is right here, and that's on the far right. So its ionization energy within the same period. This is energy level number 2. This is energy number 1. Down here, energy level number 3. Okay, and 4, and 5, and 6. Oh, no, this is 6, and I can just show all of it. All right, and so we shoot across periodic table, and we come to sodium right here. And then the general trend as we go across, so we hit argon. The long tip of each one are all the noble gases, okay? And as we go across the periodic table, the energy level is much greater compared to what is the first element of that period. Now, the general trend is our slope tends to kind of scale down. Okay, starts like that, very steep, and starts to move here. Why? If you think about it, we start getting into much bigger elements here, krypton and xenon, radon, much bigger radon. We're already at number 86 here, and this is number 86 elements. And as we get bigger and bigger, those outermost electrons, okay, now are in the 4th, 5th, 6th energy level. They're further away from the nucleus, so they tend to interact much less energy-wise as the element gets bigger. So the trend is very consistent with the size as that slope of the line starts to drop. Okay, so eventually basically plans out, but there's really no difference as far as very little difference as far as ionization energy. because the size of the elements, they're so big and they're not interacting as strongly with the outermost electrons compared to the smaller elements. Okay, so that's our general ionization energy trend. Now, you might be asked questions like, which has a larger IE and why? So here we're comparing, which is, we can also have the question, which has a larger IE and a larger radius for the following. Question like that can easily pop up. In this case, we're looking at chlorine, aluminum, and magnesium. They're all in the same period, okay? And so the IE for the chlorine would be much greater than aluminum and magnesium. It's going across the table for two reasons, really, because it's the same as we go across, we're picking up that nuclear force, that nuclear charge, and those electrons are being held down closer, hence the radius gets smaller. And second of all, chlorine is a nonmetal, and obviously aluminum and magnesium are metals. And as I stated before, nonmetals will always have a higher ionization energy when we are comparing metals. Okay, in this case, we had two metals, so this would be like, boom, automatically. The chlorine has a higher ionization energy. If they were both, all three of them were nonmetals, then we have to find where they're at on the product table relative to each other, and then determine who is, okay, who has a higher ionization energy. In this scenario, the question here, so in this case, for question number one, chlorine has a high ionization energy and the smaller radius, right? Smaller and the smaller radius. Now, with respect to this next group here, we're going down the periodic table, okay? All of them are metals. So we don't have any nonmetals here to compare, and they're all in the same group. And now we think about, all right, think about the radius. And lithium, being the smaller of the three, would have a higher ionization energy simply because its electron, and all three of them share 1 billionth electron, that property, one billionth electron, but lithium's one lone electron is much closer to the nucleus, okay, than the others, and hence is held on much tighter, and hence requires more energy to get rid of it. All right. So again, we have a additional video on ionization energy. Don't forget to read that. Now, this concept here is very important, because not to say that ionization energy is not important, but this one we're going to see this again, okay? Because it definitely affects what type of bond compounds make, okay? And this property is called electronegativity. Now, how they differ with ionization energy is this. IE deals with this lone element itself, okay? EN deals with bonded elements, okay? And what that is a measure of an atom's ability to pull electrons onto itself. We're going to learn that when these elements form bonds, specifically when nonmetals form bonds with each other, there's going to be a sharing of electrons to make that bond. It's going to make either one bond, two bonds, or three bonds. More on that later on. But that sharing may be an equal sharing or an unequal sharing, which then affects the properties of that bond, which then affects the properties of that molecule, okay? And so think of it as a magnet, if you will, where one element has a lot more magnetic force and is pulling the electrons, which are negative charged, onto itself, okay? Now, fluorine, of all the elements there that we have, fluorine is the most electronegative element that we have. And so whenever you see fluorine bonded to something, the question to the answer, the answer to the question, in that bond, which direction are electrons being pulled? You don't even have to look anything up, because fluorine pulls those electrons much greater onto itself than any of the other elements. And the general trend of this electronegativity is all relative to chlorine. Chlorine is the most electronegative, so that's our benchmark. So if I'm going to compare, let's say, carbon to nitrogen, and I'm looking at a bond between carbon and nitrogen, well, I need to know, the question may be, well, who's pulling the electrons greater, nitrogen or carbon? And to answer that, I first find their position relative to fluorine, okay? Nitrogen is much closer to fluorine than carbon. Therefore, nitrogen is a lot more electronegative than carbon, okay? Therefore, it tends to pull the electrons onto itself much greater than carbon, and we have an unequal bond associated with this scenario, okay? And that causes it to be called a certain type of bond, which we're going to discuss at length later on, which then affects the properties we can predict based on that bond, properties of that molecule, okay? Noble gases, obviously, you know, first of all, they don't form bonds, okay? And they don't react because, again, their valence electrons are all done with. We're full, they're happy, and so forth, okay? So don't forget about electronegativity. It will come back time and time and time again when we start talking about putting these compounds together to make molecules and so forth. And then it would also allow us, let me explain how important this is. Once we predict what type of bond we're dealing with, then we can look at the whole molecule and predict what type of property that whole molecule has. And now we can do predictions of things like boiling points and melting points, and other physical predictions when we do a compare and contrast of two different molecules, okay? All right, well, that ends chapter 6. Congratulations, 6 down. It's just a few more to go, right? Got about 9 more to go. All right, any questions at this point? All right, well, this brings us to chemical bonding. Okay, oh, yeah, the question, here's a question up here. Tuesday is the exam. Okay. All right. Any other questions? You're welcome. Covering chapters 4, 5, 6, 7, 8, 9, 10, right? No, just 4, 5, and 6. Okay. Let's talk about chemical bonding, but let's kind of rehash it. Hopefully what we're trying to do is kind of put everything together. Okay, we're trying to have a flow, so we start putting compounds together, and these compounds start to react with each other. And so we've been talking about, obviously we talked about converting units, and that was basically to kind of show you how to do that with a particular technique, because we're going to use that technique down the road here when we start doing calculations for chemical reactions, okay? And then we jumped into the elements themselves and start learning about some properties of elements. being able to determine who are the metals, who's the non-metals, okay? Because that's going to help us with respect to the type of compound that these elements create when they are put together with other elements, okay? We talked about the ions, what kind of charge these elements have. Some metals have charges of a +1, +2, and +3. The metals always lose electrons, hence the plus charge. Non-metals gain electrons, and then we talked about what type of charge they would have once they became ions and gained electrons, and that can vary from -3, -2, -1 charge, okay? So now we're going to start talking about the type of bond and how they come together. And I kind of introduced that a bit earlier. We're going to get more into more detail. Now, don't forget the shapes table. Okay, if you're not printed that, you will need to print that, because the shapes table will be utilized quite a bit. Let me see here. Bear with me for 1 second. I thought I had it here. Bear with me for a second. I thought I loaded up the shapes table, but let me get it. Okay. Okay, so the shapes table, not only the periodic table we're going to use, but the shapes table, which had a lot of other information, but more importantly, this particular table, which we're going to utilize the first column, which is called the general formula, labeled A, B, E. Those aren't actual compounds. They're just a general formula, A, B, and E, where A represents the central atom, okay? And then B and E represent what is attached to the central atom. And from that information, once we determine what the general formula is, then now we know the molecular geometry, which that is a kind of a three-dimensional picture of the AB4 general formula, which has a specific name for it, okay? And then what we also list is what's called the bond angle. And that bond angle is the distance between. So we have the central atom here, and then we have, maybe these could be hydrogens, 4 hydrogens bonded to the central atom, okay? And keep in mind, this line here, I want you to think about this, this line here represents a bond, okay? It's a bond there. And in that bond, we draw a line, but we can also draw 2 dots. Okay, so it's or 2 dots or a straight line. And that line represents 2 electrons that are being shared between the central atom and whatever else is bonded to the central atom. But they're electrons, and there's 4 of them here. Okay, being electrons, there's, count the number of bonds around the central atom. There's 4 bonds. Each bond has 2 electrons. Guess what? 8 electrons around the central atom, that magical 8. And being negatively charged, they are separated from each other as much as they can, given the space that they're in. And so that's the configuration that they end up with when you got 4 moieties bonded to a central atom. We call that tetrahedral. That particular geometry is pretty, I wouldn't say it's very common molecular geometry all around us, okay? And then we kind of use that as a reference guide for the other one. So once we figure out the general formula, we figure out its geometry. Now the E, I said EA is the central atom, whatever it may be. B is whatever's bonded to the central atom, okay? E is lone pair of electrons, which are represented here by these two dots. What we can have at times in the central atom are two lone pair of electrons that are not bonded to anything else, but they're sitting in the central atom. And we'll be able to determine how many of these lone pair we have. We can have either one or we can have two of them, okay? Like this one there. And that, in effect, results in a big change in the geometry, which affects the properties of the molecule. Okay? All right. So, more on that with due time. All right. We talked about noble gases and how they're octet, right? So the goal here in making bonds is the octet rule. And the duet rule, but only for hydrogen and helium. So what that means is this: hydrogen will always, you're going to see a lot of hydrogen bonded to something. And hydrogen will always only have one bond, one line, okay? You won't find hydrogen with two lines or three lines attached to it. They're always going to be one, because it has to follow the duet rule with two electrons. And so what do I mean by that? Okay, I could have carbon and the line represents hydrogen. Okay, this line represents a bond. And we're going to have a lot more talk about what type of bond that is. Okay, in terms. So this line can be written like C, then two dots. It's the same thing. These two dots represent that line. Okay. And that's it. I can't put any more. The rule for hydrogen is the duet. Those two electrons are being shared between the carbon and the hydrogen, and therefore count toward both, each one, when we are making sure the octet is full. Let's take this example here where we have carbon with 4 hydrogens bonded to it. Okay. Notice that each line represents 2 electrons. So we have a total of 8 electrons. There's 4 lines, 2 of them. So we got 8 electrons around carbon. Each one of those 2 electrons are being shared with hydrogen. So when we count them as being shared. So these 2 here count for the hydrogen and the carbon. Okay. And there's 8 around carbon, hence the octet. So when we start writing formulas, we always have to make sure that the octet is fulfilled, all right? And the duet is fulfilled for hydrogens. Obviously, we talked about this at length. Metals lose electrons and when they become cations, and nonmetals gain electrons when they become anions, okay? All right, now, when we have a combination of a metal and a nonmetal, okay, what we have is an ionic compound. Specifically, what we also have is an ionic bond. Okay, so an example of this would be the ion sodium, which has a plus charge, and the anion chloride, which has a negative charge. Okay, so these two are attracted to each other, and we write the formula as, without the charges, as NaCl. Okay, the fact that we have a metal and a nonmetal combination tells us that we have an ionic compound with an ionic bond. Furthermore, there's no sharing of electrons here, like I just showed you between carbon and hydrogen. Okay, so in ionic bonds, there is no sharing of electrons. They're simply an attraction like magnets, if you will, analogous to magnets. Sodium represents one magnet, chloride represents another magnet. Bam, they come together and they are attracted to each other. There's no sharing of electrons, but nevertheless, we call it an ionic bond, okay? We know that you can take those two magnets and you can break them apart, right? Well, guess what? There's a property about ionic bonds, ionic compounds. When we take them and we put them in water and dissolve them in water, they break apart, they dissociate. Now, not all of them dissociate 100%. Some of them dissociate 100%, some of them maybe 90%, not as much, but all of them, every one of them will dissociate a certain amount and go into solution and break apart back to the ion. Okay, so I can draw an arrow when I put them in water like this. The other type of compound that we're going to talk about, which is molecular, when we put them in water, guess what? They don't break apart because they're sharing electrons, okay? They're sharing electrons. All right, so when we put these together, ionic ions together, we have to put them together with positive and negative. So you won't see two positives bonded together, okay? Because they repel. It's an opposite attraction kind of thing going on. And so calcium would be bonded with the bromide, okay? And the bromine and lithium would be bonded with each other, but you will not see the calcium and the lithium ions bonded with each other. Okay, so ionic compounds are some limited examples, but nevertheless, you know, here we have sodium chloride, potassium, A is potassium, and Cl is chloride. Now, chlorine, remember, the chlorine, once it becomes an ion, changes the name to chloride. So that is potassium chloride. Same is true with bromine. That is not bromine because you see a subscript there. The fact that you see calcium written first, then followed by the BRs, tells you have an ionic compound. You don't, this is not bromine. Bromine is one of the diatomic. That's not, okay? You got calcium first and then followed by two BRs, which are ionic, which now the name changes to bromide. So it's calcium bromide, okay? So here, if you're not sure about which element's a metal, which is a non-metal, this is where you have to check that table I sent before, the periodic table, and look at the stair step. To the left of the stair step are the metals, with the exception of hydrogen, and to the right of that are the non-metals. Okay, and we know that potassium is a metal, calcium is a metal, and then the respective halogens are non-metals. So we have ionic compounds or ionic bonds. Here's the key right there. Metal, non-metal combination. When you have the combination of a non-metal, non-metal combination, we have what are called covalent compounds using covalent bonds. If you break the term down, covalent, you think about it, then valent coming from valence electrons. Well, what's happening is they're co-sharing, they're sharing their respective valence electrons to form a bond, okay? Covalent, and how we identify them is the fact that it's a combination of two nonmetals. So all of the all 7 diatomic elements are covalent compounds, okay? Because it's two nonmetals. But things like H2O, water, carbon dioxide, those are other examples, further examples of covalent compounds, okay? And like I mentioned earlier, one of the main differences between physical properties between ionic And covalent is when we simply put them in water. Ionic compounds tend to dissociate a variety of different degrees, okay? Some 100%, some much, much, much less. But nevertheless, there's always some of it going into solution, breaking up into the respective ions. Now, that part is important. We'll come back to that. Covalent compounds, when we put them in water, they will not break up. They stay intact in their formula, okay? They're not ionic. There's one exception, and we'll get to that in a while, but I'll tell you now, they're organic acids like nitric acid, acetic acid. Those are covalent compounds, but because of their acids, they will dissociate, okay? But we have a whole chapter on acids. We'll get to that. Okay, so we're going to be talking about ionic compounds and then how to make ionic formulas. Okay, so we have this formula here, CaBr2. Now, as a general rule, and I repeat, as a general rule, the atom written first in the formula is generally the central atom, and then what follows is essentially bonded to the central atom, okay? And so one way to look at this is we have calcium here in the middle, and then bonded to that we have, actually more attracted to it, but I'm gonna put a line there just to represent. Let me do it this way. We have calcium in the central with a +2, and we got one bromide over here with a -1, one bromide with a -1. Okay, hopefully you're picking up on this here, because you can see that each bromide has a -1. How do you know it's got a -1 charge? Look at its position in our periodic table. It's in group 7. It will pick up one electron. Picking up one electron gives it a negative charge. Okay. How do I know calcium is a +2? It's a metal. When it becomes ionic, find it in the periodic table. It is in group 2A. It's 2 valence electrons. It's a metal. It's going to lose those 2 electrons, resulting in a +2 charge in ionic form. Okay. When I put these together, I need 2 negatives to cancel the +2 of calcium. And that's why the formula for calcium bromide is CaBr2. Okay. All right, let me clear here. So, in ionic compounds, the thing to remember when we start putting them together is this. There's a very good generic formula for you at this point. I'm going to add I'm going to change it a little bit as we get down the road, but it's straightforward. When we're making formulas of ionic compounds, the number of cations plus the number of anions must equal 0. Okay, so the total number of cations positive charge and the total number of anions negative charge, you must have an equal number of each so that they end up with a negative overall charge. Okay, and hence you saw how we had calcium +2, and then we had 2 bromides. Okay, and so those 2 negatives cancel out the +2 for the calcium. Right. Well, here they're asking you to identify which ones are ionic of these. Okay, now you may not know what they are. That's okay. But you do know what defines an ionic compound. You recall what defines an ionic compound? Remember what defines an ionic compound. How can I look at a formula and determine whether it's ionic? What is the definition of an ionic compound? It's a metal and a non-metal. Correct. Both here is correct. And so if I'm given a list here, the straightforward step is to go in there and say, okay, who's a metal, who's a non-metal? And that is why it's important about that periodic table that broke down the metals and the non-metals, okay? All right, so we look at KBr. Obviously, potassium is a metal and bromide is a non-metal. So definitely this is an ionic compound. The next one, you may not know what it is. That's okay. I'm going to tell you in a bit what it is, but you got sulfur and oxygen. Okay, two non-metals. So definitely this is not ionic. The next one is HCl. Again, two non-metals, not that. Then we got bromine, two non-metals. So that's not ionic. And then finally, we got, not finally, but we got carbon and oxygen. Obviously not metal. And then we got the last one where we have magnesium and chloride. So for sure, those two are ionic. Okay. What does that tell you about the others then? The other ones are non-ionic or covalent, right? Covalent compounds. This one, by the way, is called sulfur trioxide. If you ever, occasionally depends on the car, and you're behind a car and you smell like and this exhaust is a rotten egg odor. That's what you're smelling, sulfur trioxide coming out of the vehicle in front of you. That gets up in the atmosphere, reacts with moisture up there, and then proceeds with a number of steps to form sulfuric acid, which is an acid, and creates acid rain. And the next time it rains, it comes down, hits the soil, and it causes the soil to become acidic because of the sulfuric acid. Then once the soil is acidic, it causes the metals in the soil, the heavy metals that can be dangerous, to go in solution and then contaminate the waters. All right, the next one here is called hydrochloric acid. Okay, all of you right now have that in your stomach. Okay, that is the acid that is in your stomach that used to break down components, to break down your lungs and so forth. And then the Br2 is simply called bromine. Okay, not anything diet, just happens to be diatomic. And then, of course, the infamous CO2, which is carbon dioxide. Carbon dioxide. Notice the trend here in naming compounds. I want you to pick up on something. Okay. We just established that CO2 is not ionic, it is covalent. But the name that we give it is called carbon dioxide. Okay. As compared to MgCl2, which is simply called magnesium chloride. Notice that it's not called dichloride, okay? And so there's another major difference between ionic compounds and covalent compounds, and that is with respect to naming them. We don't use prefixes when we are dealing with ionic compounds and dealing with their names, okay? You may see in the label sometimes of something, you'll see the dichloride, something. That is totally 100% incorrect. That's I think a lot of that's marketing or something. I don't know, but that's not correct as far as naming that compound. All right, so with respect to ionic compounds, as I stated, there are the coming together of ions, okay? That means a full positive charge and a full negative charge. And so sodium, being a metal, will lose an electron and form Na, the sodium ion. The chloride atom will pick up an electron because it's a nonmetal to give us a chloride ion, okay? Notice the relative radius size. Here's sodium atom compared to the sodium ion. That's consistent with what has happened. We talked about this. Remember, we said sodium atom has one valence electron in the third energy level. Well, when it becomes ionic, that third energy level is empty, okay? And the next energy level that sodium has now that is full is the second energy level, plus it has a plus charge. Compared to chloride that has one empty spot for an electron, it picks up an electron to form the chloride from chlorine, okay? And now has more negatives in the orbital, which makes it, they repel each other. So now the radius of the ion of chlorine is bigger, okay? So a general trend is this. The ion of a metal, the ion of a metal generally is smaller in ionic form. The radius, I should say, the radius of a metal element is smaller in ionic form, and in contrast, for nonmetals, the ionic form is larger in diameter, okay? Okay, so let's consider magnesium and sulfur atoms. And then we want to consider the magnesium and the sulfur ions, okay? We went through this before, but we'll go over it again, okay, just to demonstrate. Magnesium atom had change the color. Second. And the ion both have 12 protons, okay? Where they differ is in the number of electrons because the ion has lost 2. Sulfur and the sulfur ion, okay, they have 16 protons. Where they differ is in the number of electrons. Also, what happens is this, the ion becomes, name change becomes sulfide. Okay, so we went from sulfur to sulfide. Okay, so we want to put together a formula concerning the ions of magnesium and.
Why you so?
Hello?
Low, tough.
Hello? Did somebody had a question? Yeah, you had a question? All right, so if you're asked a question to make a formula starting with the magnesium and sulfur ions, the first step is this. You got to put them in ionic form first, okay? And so you take magnesium, you put it in ionic form, we end up with Mg plus 2, okay? We know that, why? Because we know magnesium, the element is in group 2. So in ionic form, it's a metal, it's going to lose 2 electrons. Sulfur is in group 7, okay? Group 7, so it's going to pick up 2 electrons and end up with a, hold on one second, negative charge. Okay, now we're going to put them together because remember what I stated? When you put them together, the number of cations must equal the number of anions. So magnesium is a +2, the sulfide now is a -2. We can write the formula straightforward and just write MgS. The name is magnesium sulfide. notice something. I didn't say sulfur, okay? Magnesium and sulfur would be incorrect in the name because the sulfur became sulfide. All the nonmetals, you might come familiar with that. All the nonmetals, when they become ionic, we change the name from the name and we add the suffix IDE. Okay. Okay, so recap, we talked about ionic sizes. Some refresher information here for you. Cations lose electrons, they have more protons. They pull the electrons closer to this, so the nucleus gets smaller. Okay, plus they lost electrons, so the next layer in, the next valence shell is much the next energy in. Whereas anions gain electrons, more electrons, they repel each other, so they pull away, they push away, and the nucleus gets bigger. Okay. Now, true or false regarding the ionic bond between the aluminum and the iodine. Okay. Notice between the ionic bond between aluminum and iodine. The aluminum atom loses electrons and the iodine atom gains electrons. Is that a true statement? What do you guys think? Or is it the other way around? Is it iodine gains electrons or loses electrons? That's a true statement. Metal, aluminums lose electrons. Iodine is a non-metal, they gain electrons. Okay, now think about this one. The aluminum atom is larger in radius than the aluminum ion. Okay. That would be true, okay, because the aluminum lost the electrons, the outermost shell. And now the next shell in is the one with the octet. Plus, as I stated in the previous slide, in losing electrons, there are more positive protons than there are negative electrons. And so that means those electrons that are left over are going to be pulled in even tighter. The iodine atom is smaller in radius than the iodine. And again, that is a true statement. Okay. The aluminum and the iodide ions, okay, that's important. It said iodide ions form a bond by attraction, and that is true. It is a full positive and a full negative charge that come together and being attracted, much like two magnets coming together. Okay. Not much to say about metallic bonding. Basically, just to say that electrons are just a sea, a whole bunch of, metals have a whole large number of electrons on the surface. And therefore, because of that, the metals are very good conductors of electricity and also very good conductors of heat. All right. Now, let's talk about covalent bonds. Whereas we had with ionic bonds, we had an electrical, what we call an attraction between them, between the ions to come together. Covalent compounds actually have a true actual bond where they are sharing electrons. Now we have three types of bonds, okay? We have a single bond, which I denoted earlier by a simple line. So I could write it either as two dots, which represent a single bond, or I can draw it as a line, okay? So this is a single bond, SB. A double bond, I can write with two lines as follows, which represents 4 electrons. So that is a double bond. And then we have a triple bond, which I can denote by 3 lines, or I can put in 6 electrons. And that is a triple bond, okay? So a triple bond has 6 electrons, double bond has a total of 4 electrons, and a single bond has 2 electrons, okay? And these electrons, keep in mind, are shared. They're being shared with the other atom. Okay? So we have carbon dioxide, which is a covalent bond. We're going to draw this structure. We're going to come up with a structure, show you how we came up with this. But carbon dioxide actually is carbon in the middle. Notice we draw right C first, followed by what follows. So carbon is a central atom, okay? And then the oxygens are bonded to the central atom. And we're going to learn that there are two double bonds here between the carbon and oxygen on the right, and two double bonds, let me restate that, a double bond between the carbon and the oxygens on both left and right. Another example of a covalent bond is H2O, or good old-fashioned water. Okay. I talked about this already. So we got a single bond, double bonds, and triple bonds. Now, in general, single bonds, well, I shouldn't say in general, single bonds, when we compare the strength of bonds between single, double, and triple, the single bonds are generally happen to be longer and the weakest, okay? The weakest as far as energy is concerned. Whereas the triple bonds tend to be shorter, and we mean by shorter meaning the distance between the two elements that are put together, they're sharing that bond, but they happen to be the strongest, okay? A good example would be, question. Oh yeah, we're gonna learn about the electrons and how many they share. Good question. So right now, we're just introducing what the single, the triple bond, and the double bonds, how do we represent that? But basically, when you see one line and there's two elements bonded to that one line, that tells you that those two electrons are being shared with that single bond. And if you see two bonds, two lines, I should say, that double bond, there are 4 electrons being shared, okay, in that bond, and then triple bond will have 6 electrons. Okay. All right. Now, with respect to strength, the single bonds are the longest and the weakest. And a good example about this one, you know, I'm sure everybody's seen or used butane. You know, butane lighter, for example, with a little flick your bic kind of thing. Well, okay, you can burn it, ignite it, it's flammable, it's a hydrocarbon, it will burn. But it can't cut metal. But if you take something that's called acetylene, which I'm just going to quickly draw the structure, which is basically a carbon, 2 carbons with a triple bond between them. You know, this acetylene has a lot of energy. In fact, so much that, you know, it will cut metal. You're going to acetylene torture. That's how much energy is in there. All right. All right. Well, tell you what. Let me stop it here. I see the time here, and we're going to continue with this on Tuesday, unless there's questions concerning chapters 4, 5, and 6. I'm going to stop it here. Slide 7. Well,